maybe because you overcame challenges on those projects, or you did something innovative. This case history I'm going to share with you is my trophy project. This is the world's largest self-anchored suspension bridge. If you're wondering what a self-anchored suspension bridge is, it's a suspension bridge, except the cables are tied to the ends of the deck, not in the ground. This self-anchored suspension bridge is part of the San Francisco-Oakland Bay Bridge East Span Replacement Project. So it's only one component of it. And this unique design came about through a referendum and a design competition. The winning design was by T.Y. Lin, very famous California bridge company. They designed this bridge, but they did not design how to construct it. So the construction was led as a design-build contract. The contractor had to figure out how to construct the temporary works to build this bridge. And the temporary works was a major component of this construction. And that's where Klonkrip & Berger came in. We provided erection engineering services on this project for the temporary works, and I was the lead geotechnical engineer on it. I'm going to focus on the geotechnical aspects of the temporary works, but I'll show you how they actually constructed this bridge. Many of you will be familiar with San Francisco. It's a peninsula on the west coast of California. It's famous for many things. San Francisco, the Golden Gate Bridge, the Alcatraz prison, the Silicon Valley in San Jose to the south there. It's got the Pacific Ocean on one side and the bay on the other side. It's also famous for this San Francisco-Oakland Bay Bridge that links San Francisco downtown to Oakland. And if you also look at this map here, you can see the linear trends, the northwest, southeast mountain trends. Those define 7 active faults in this area. So as you know, San Francisco is famous for earthquakes. This was the original bridge, San Francisco-Oakland Bay Bridge, built in 1936. It was built by American Bridge Company out of Pittsburgh. It's the same company that built this self-anchored suspension bridge. It's 7.5 kilometers long, 2 parts to it. There's a west span, which is San Francisco to the middle there. There's an island called Yerba Buena Island. All it is a piece of rock. And then from there, it goes to Oakland. That's the east span. And just north of the rock island, Yerba Buena Island, is Treasure Island. It's a man-made field island. It used to be a naval facilities, but not anymore. This is a view of the west span. San Francisco on the left, the island on the right, and you can see it's a series of 2 suspension bridges, traditional ones in series, and in the middle there is the central anchor block for these 2 bridges. As well, they anchored at the ends. This was the old east span. It's a steel cantilevered steel bridge. It's double deck, just like the other suspension bridges as well. It's 2 decks, and they go to inside the Yerba Buena Island. It's also 2 decks. That island apparently it's 20 meters wide, and that was considered the largest tunnel bore in the world. And it probably might still be. And they have 2 levels of traffic through it. Double decks, 5 lanes on each deck, and they had 280,000 vehicles per day at that time. In 1989, a lot of you probably heard of it, Loma Prieta came, and that upper deck collapsed or fell down, and some cars went over it. 1 person died from this. Now, as well, if you go to the right of it, would be Oakland, and this freeway, double deck, again, several parts of it collapsed, and that killed quite a few people, unfortunately. So they decided to replace this east span, this 3.5 kilometer long bridge. This is rendering of the new east span. It's just to the north of the old span. 3.5 kilometers long. It took them 12 years to construct, and they completed in 2013. 6.4 billion. It was the largest, probably still is the largest public works in California history. The main contracts were laid out in 3 parts. The Skyway section is from Oakland, which is to the right. Most of it is the segmental concrete box girder bridge, fairly traditional. Then you can see in the middle there is the self-anchored suspension bridge. And the third part is another span, about half a kilometer long. It's called a Yerba Buena Island transition. So it allows them to change from the double deck to side-by-side span. So the new east span is now side-by-side. When you drive over it, you can see a lot more than it used to be when one was on top of the other. These are some of the details on the suspension bridge. Designer was T.Y. Lin with Moffett Nickel for the whole east span project. It's only one tower, 160 meters high. It's asymmetrical. The long span out towards the water is 385 meters, and the short span is only 180 meters. Only one cable, even though it may not look like it. The main cable is only 1.8 meters diameter, and it's anchored to the deck, but we're going to talk more about it later on. And the vertical suspenders are kind of splayed out because of the curvature. It's got 2 hollow orthotropic steel box girders. So those are the decks. In effect, it's actually 2 bridges, and they're connected with cross beams. Each deck has 5 lanes, as well as some emergency shoulders. Plus, there's a cantilever on the south side that allow pedestrian and bicycles to go from Oakland to this island. And that's it. You can't go further than that. This is schematic of the self-anchored suspension bridge. American Bridge Scope and Floor, which is a joint venture that we work with. Scope is that part. It's the bridge and one tower, the main tower. They did not have to worry about the foundations for the 2 end piers and the piers themselves, or the foundation for the main tower. They were installed by the previous contractor. So that's how they broke it up. American Bridge only had this tower and the bridge itself. If you look at the bottom, you can see the cable. It's anchored at the east end. Remember, it's one cable. It's looped around the west end, which is on the left, right? And back to the east end. It's not, they don't cross on top of the tower. With this design, all the vertical loads essentially go down through that tower. The tower carries all the vertical load. The horizontal forces on the cable put this bridge into compression, so the decks are always in compression once you've loaded it. Very unique design. And you can see how simple it is, this scope. And this is 1.4 billion just to build that suspension part and one tower. No foundations. So the question is, how do we construct a self-anchored suspension bridge? Remember, the decks need the cables, but the cable also need to tie into the deck. So it's almost like we're trying to pull ourselves out on our bootstrap. You need one bridge to build another bridge. And so we designed this temporary bridge. There's 6 pairs of towers and pile foundations. All 6 of them were piled. They're the trusses end to end. It's about 600 meters long. And we also designed the cradles, because when the box girders arrive here, it has to be moved from the water to the land or to the other parts. So that's part of this design. And I just mentioned that. Foundations, towers, trusses. Let's look at the geology of this site. Yerba Buena Island on the left, San Francisco is far left. The island is rock, it's sedimentary rock, interbedded sandstone, siltstone, claystone, typically a little bit weather on top and then stronger with depth. But it dips down fairly quickly into the bay towards Oakland to the right. And you can see it's underlain by deep sediments, clays, sands, overlying bedrock. There's some even softer young bay mud further to the east. Now we'll talk about, before we get back to this foundation, we'll talk about how they constructed this bridge, because it's so unique and I found it fascinating. So I thought I'll share that with you and then I'll tell you what we did for the temporary works. So once all the pile foundations were in for the temporary towers, the towers from land went up. The trusses were put on the towers, and you can see some of the offshore foundations there. And then they started going further out towards the offshore. That tower, you can see, is quite slender. The structural engineers call that a tubular eccentrically braced frame, or EBF. It was developed by Professor Michel Bruno in sunny Buffalo. It's very good for earthquake loading because all these towers had to be designed for earthquake, storm, as well as the water ship impact. So those were big dynamic forces. The trusses that were placed, they're 8.5 meters high. So you can get the sense of the size that they were dealing with. And then finally, towers, trusses, all in place. So this is the temporary bridge. That's only one part of it, the water part. There's 25,000 tons of steel on this temporary bridge alone. Now, they needed a special crane. So they got it purposely built in China. That blue rig you see there, marine crane, it's got double boom, 100 meters long, and the capacity is 1,800 tons. Purpose built just for this project, across the Atlantic, the Pacific, on this semi-submersible. It's a float-on, float-off ship, so it picked that up, that marine crane, and then brought it across the Pacific to San Francisco. So once the temporary bridge was in place, then they started bringing in the box girders, the deck. This first one, 1,000 tons. That dimension across is 27 meters. The height is 5.5 meters, and the length of that first segment is 45 meters. You can tell by the size of the people there. It's sitting on a cradle. Each segment had one cradle for it. Here's a view of the jacking system. So it's like a double jack push cart system that pushes the cradle to place from the water. The first one goes all the way to land. Fairly slow process. Took them over a day, about a day and a half, to get the first segment all the way to the end, just slowly pushing itself. It's a view of that deck element, that box girder going into position. Altogether, there were 28 pieces, 14 on eastbound lane and 14 on the westbound lane. This is a view of the towers or the bridge, temporary bridge, from the water looking west towards Yerba Buena Island. And you can see some of the elements of box girders were at the far end. This is a view from towards the land, again in this, going west, underneath the deck. You can see some of the towers on land. One of the things we had to do, especially in California, they're so concerned about protecting the environment. We had to minimize the disturbance because everything else had to come down after the whole temporary bridge had to be removed after this, and the land restored. Certain areas we cannot touch. This is a view looking under on the decks or box girders, and then you can see the cross beam. They are 30 meters apart. Here's a bird's eye view with a few pieces already in place. And that is where the single tower, that main tower, is located. And it's located in between the two bridges. Once the decks were, or while the decks were being constructed or placed, then they started the tower. They also need temporary tower, and they brought in segments. The tower, even though I mentioned it's one single tower, it's actually made up of 4 pieces. They're tapered. Here it's looking down. So you can see there are 4 pieces of towers. They placed these in 5 lengths, 5 lifts. The first 4 were these, and the last piece, the 5th one, is what they call the crown, or it's got a saddle in it. It's got a saddle to accommodate the cable. So this is the bottom left is the 4th lift being put in place. So they had a jacking system, almost like a self-launching jack that keeps going up on this to be able to get this in place. Obviously, they had to leave gaps to allow these things to be placed. All the segments have to be sequential. There's certain sequence to it. So towers, and then finally, this is the last 2 segments going in. Tower was completed. You can see a cable, but that's only a temporary cable for construction, or a catwalk, to allow them to be able to install the permanent cable. This is a skyway section. So it's the segmental box, concrete box girder bridge. It was all constructed about 2 years ahead of this. There was a bit of a problem in scheduling, such that they had this sitting there for a while until the self-anchored suspension bridge was being built. That's the self-anchored suspension span, only about less than 600 meters long. And then the far end is another 500-meter long transition section. Okay, so once the decks, towers, all in place, then you have to look at the cable. And the cable, the way they did it was to start on the northeast at the anchor end. Cable went up to the tower, then towards the west end, wrap around underneath the deck on the west end, came back up to the tower without crossing, and then back out to the southeast end. And it's relatively simple in concept. But the cable itself, even though it's one, it's actually made up of 137 strands or bundles. And each strand has 127 parallel wires. They're not allowed to cross. They were parallel. Amazingly. Now, apparently it's stronger that way. So they have to install this. And the way they did it is each strand, each one of those 137 arrive in a reel, a spool like this. And there's 126 parallel cables you can see there. That frame is a launching. So this is at the northeast end. There's a launching system frame to get this and pick up by one of these lift. So this lift picks up one strand and travel up the tower. Here's a view going up to the main tower, and then comes down on towards the west on the north side. And you can see there's several strands already in place on this one. Loop underneath the west ends, came back up towards the tower, and goes down to the southeast end at the anchor point. The 2 anchor points are below that, and they look like this. There's a board, a numbered board. They know exactly which strand to place to anchor in place. So each one of those decks had this underneath where it's individually anchored in place. Once the cables, the 137 strands were in place, they sent a machine called a compactor, kind of wrap around the cable, and it traveled and compress it. So it's a compactor or compressor to compress to look like one. Then they tied some wires. I think these are special zinc coated stuff, and then they painted to prevent corrosion. So it looks like one cable, but it was placed 137 times around the place. All parallel wires, 17,000 wires in that cable. Once your cable is in place, and there's no load on it yet, you have to get the suspenders. And remember, the suspenders are not the traditional vertical ones. These are split out at an angle. So they have to locate those accurately. And each of the suspenders came down to the deck underneath it. And there's a jacking system. So there's a jack on every one of those suspenders. Altogether, there were 114 saddles. So that's like the saddle they attached to it, 114 of them. It helps to keep the cable together, plus it's the anchor point for those suspenders. So they have to have it accurately, because once you load, this is not loaded yet, when you load it up, the cable is going to sag. So those things have to be very accurate. Each suspenders go, you can see them in place. Then they went to the side underneath it, and every one of them had individual jacks, over 100 jacks on this bridge to transfer the load. Then they started load transfer by jacking them in 3 phases. All the load then got transferred to this tower. Those box girders, the load, total load is 35,000 tons. All went up on this tower. And then finally, if you look under the deck, at load transfer, it was clear of that temporary bridge and the those frames underneath it. So basically, they had their load transfer on November 2012. And us as a designer of temporary works, it was a big relief, because we don't have liability anymore after that. Now, the fun part is, once it was in place, they started dismantling the temporary bridge. That's part of it. So we're looking underneath towards Yerba Buena Island at the far end of it. You can see the temporary bridge is all there. And then they started taking down the trusses. They removed the towers, and they even removed the piles. So they had to remove everything. They're allowed to leave if it's more than 1 meter below grade, below mud line. So everything 1 meter below and up had to be removed. This was a completed bridge just the day before they opened it. And you can see how graceful it is. The old bridge is on the left or south side. This is looking towards Yerba Buena Island. And then this is again down from the water side, a view of the completed bridge with the old bridge, which is now gone. It took them a few years to dismantle this one. And you can see how graceful it is. It's fairly simple design, but it was quite interesting or quite tricky to construct. So now we're going to talk maybe a bit of an anticlimax now about the foundations for temporary works, because they're not there anymore. Okay, for that, I mentioned earlier, we had 6 pairs of towers, eastbound, westbound. Towers A, B, and C were on land on Yerba Buena Island. A and B were on top, and then C was near the water edge. What we decided to do is we use micropiles where the towers had to be on the slope, just because of the logistics. We couldn't move it too far. And for the relatively flat ground, we were able to use drill shafts. Tower D, which is the first one, which is the main tower, for the temporary works or temporary towers, we use open-ended steel pipe piles. We drove it into rock. So we were relying, we needed capacity in rock, open-ended. F and G are out deeper water, and we use open-ended pipe piles because of the sediments. They were driven to marine sediments, mostly, essentially friction piles. This is a view of the old bridge on the Yerba Buena Island. So you're looking southwest. Those two piers were being constructed before by another contractor. So American Bridge had to put in their alignments here. So they had to eastbound, westbound. And you can see that slope there. That was an issue. How do you place towers or bends on this slope? As well, on top of it, there was an old retaining wall of historical value that they wanted to keep. At the bottom, you can see it's something, what they call a torpedo building, also historical. We could not touch it. We could not damage it at all. So our towers had to span between those structures, and we had to put some on the slope. So towers A, B, and C on land. This is a plan view of that rock island, basically. So A and B lines were on top or on the slope, and then C is near the water edge. For the steep slope, we decided to go in micropiles. So those the red marks there, or the boxes, are the micropile foundations. And for where we had access, we use drill shafts. In the US, they like to call it cast-in drill hole piles. So it's the same concept. You drill a rock socket, you socket into rock. And again, we got eastbound and westbound lane. This is what our micropile foundation looked like. It's a one pile group, typical pile group, 8 vertical piles, but we had to carry horizontal forces as well. And hence we use horizontal micropiles at 10 degrees to the horizontal. On the section, you can see we had to make a notch. This is a 60 to 70 degree slope with a cut a notch there, and then install the vertical, horizontal micropiles, and then form the pile cap. And the only way you could do it, plus you have to put anchors. So the only way you can do it is through the top, the only practical way. And so everything was done with a crane, lowering down equipment and people to construct on this slope. At the same time, protecting that retaining wall that they've covered there. So this is a view looking at one of these working platforms suspended on a crane. Everything by hand down there, or you have to, because there's just no access. This one showing portable equipment drilling vertical holes. Again, suspended by a crane. This one shows a drilling platform, now drilling horizontally, 10 degrees to the horizontal, and then installing the micropile or like anchor. This is a view of one pile group with most of the micropiles, vertical micropiles in place. The design is shown on the left. It's a traditional 200 millimeter diameter hole. The anchor itself is 65 millimeter diameter. It's typically, because of the weathered zone, there's a case section, which is the unbonded length. And then below that is a bond length, where we had the stronger sedimentary rock that we relied on friction, a bond between the concrete and the rock for the pile capacity. We load tested every one of them because they were done by hand. You just have to be very careful. We didn't have much redundancy. So every one of them were proof tested before we loaded this. This is a view, bird's eye view, looking down at those micropile foundations. At the lower end, B1, you can see they got their rebar there. They were just starting to form. B2, they got the formwork, rebar in place. A1 is where the concrete has already been placed for the pile cap. And A2 is a drill shaft. This is our design for the drill shaft, 1.5 meter diameter shaft, upper length case because of some soil and weathered rock, rock socketed, typically up to 9 meter deep into sound rock. And we designed them to carry 17 meganewton per pile. Again, no redundancy, and hence the design had to be reasonably conservative. This is the way they install auger with a very high power torque auger rig. At the water, we had to protect the shoreline with a system to make sure it's contained, and then rebar, and then pouring concrete. So the drill shaft was fairly kind of routine because they do a lot of that in the US. Now we'll talk about the offshore piles. D was just shallow water, F and G. So on D, we had 10 to 20 meters of water. It's got 5 meters soft clay, and then you hit rock. But the good thing is the rock, the upper part, was heavily, intensely weathered, very weak. And hence we're relying on that to help us get embedment into the stronger rock beneath that. As well on Tower D, because there was an existing foundation for the main tower, we were allowed to design temporary towers only for vertical loads. The horizontal loads were transferred to the permanent pile foundation. F is in 24, 27 meter water. It's got 35 meter deep interbedded stiff to hard clays overlying the dipping rock. So both D and F had this rock that's dipping that we had to consider. In Tower G, 16 to 20 meter of water and thicker sediments, 40 meters, clays overlying sands above bedrock, up to 90 meters deep. So in Tower D, with relatively less soil and a lot and more rock that we had to get our foundations in, we decided with the drill shaft or driven piles. The US, they were a lot more comfortable with drill shaft. They were surprised that we had proposed driven piles into rock. So because there was no precedence in this kind of rock. Also, they were concerned about pile toe damage on this sloping rock. So we had to prove it out, did the usual thing, pile drivability analysis, check your stresses, check what kind of hammer do we use, because this is like offshore piling, and then determine what the criteria will be. As well, because it's so uncertain driving pile into rock and relying on the capacity, we have uncertainties. So we had to vary a lot of parameters to make sure we capture most of them. Also, is the rock going to come into the pile and form a plug, or it will just keep coming through? Those you have to consider it. As well, when you drive something hard, like into glacial till, you have to think about, will it relax? After you get your driving criteria or refusal criteria, is it going to relax with time? We were concerned it might, and so we had a backup plan to prove to Caltrans, is the Ministry of Transportation down there in California. So we had to prove to them that we do have a backup plan and that we would drill out, if we don't get the capacity, we'll drill out and put in a concrete plug to get end bearing, if that is required. So that was the kind of plan that we had to have in place for this. This is the main tower foundation is right in the middle there. That was by another contractor. We came in and we installed 8 piles for each tower. So on the north and the south of that main tower, 8 vertical piles. The piles were 1.07 meter diameter. That's 42 inch. 1.5 inch, 38 millimeter thick wall. They were driven through, I mentioned, relatively 5 meters, relatively thin soft clay, and into weathered rock until we got refusal in sound rock. The design loads were up to 13 meganewton for each pile. The two special features we put on, one is the reinforced pile tip. So the bottom 1.5 meters, we double the steel thickness. So instead of 38 millimeter, it's 76 millimeter thick. So that's 3-inch thick steel at the bottom. Now, of course, we had to worry about the stresses right above it from the thick section to the rest of the pile. We also install shear rings. So on the inside, we put in some steel rings so that in the event we need to use plan B to drill out and form a concrete plug. That's how the design was accepted by them to make sure that we have considered all this. This is a view looking east from Yerba Buena Island on Tower D. The existing foundation for the main tower is there, T1, and so we were piling on either side of it. And you can see the skyway had already been constructed a couple of years before that. You can see a hammer sitting there. This is what the hammer looks like. It's an offshore hammer. You just have to look at the size of the people. You can see how big it is. It's a MEC 500T hammer. We needed that to drive it hard into rock. And we had PDA monitoring to make sure we don't overstress the pile, as well as to check what the pile capacity would be. Here's a view of all 16 piles once we drove them. This is a view of the driving frame. So before we drove those piles, we designed this driving frame, which also became like a pile cap. So they were brought out there. We had temporary piles first, drop them on to locate them properly, and they had sleeves for these piles. So the 8 piles had sleeve in plant on that jacket to allow them to go in place. So we did have pile relaxation, something that we weren't so sure, and it turned out that was a problem we had to deal with. Initial driving, we drove them to 8 blows per inch, last inch of driving. We had one restrike 15 days later, brought out all the equipment, drove the piles, and we found relaxation. They were going easier. They were still going in, more easier than 8 blows per inch. We drove them, this time to 12 blows per inch. Then we asked for another restrike, another 15 days later. Now, these are offshore. Every restrike is expensive. It came out, and we did some more, and we had more relaxation, but less than the first time. And we redrove them again to 12 blows per inch. Now, the good thing is the capacity showed that whenever we restruck them, we had enough capacity, more than the design of 10 or 12 meganewton, or more than that. So we had those capacities, and piles had actually, during those 2 restrikes, had gone, some of them hardly moved, 225 millimeter. Some the piles went 2.4 meters. So we had to go another 2.4 meters. The question is, what is the long-term performance? Will it relax some more? We weren't sure. We had done slick durability tests on those, and we couldn't prove it. Pile relaxation is one of those fields that you kind of know it could happen when you drive hard, but it's not well understood. Our profession hasn't quite figured out yet how to predict ahead of time. So we had to decide, do we accept, when we, with the contractor, decided they're going to accept the risk in case there's more relaxation, but they're going to monitor it with the settlement in case something were to happen. So post-construction settlement for the next 2 years, 3 to 9 millimeter. So we were lucky that they performed well. And just a reminder, pile relaxation doesn't happen very often, and it's still not fully understood. There's got to be more research to try and improve on this particular phenomenon. Towers F and G were more friction piles. Settlement criterion given for the design was 25 millimeters. Settlement is all they could allow. We did pile drivability, check all the stresses, what kind of hammer to use, because they're not going into rock like Tower D. We also have to think, will they plug or will it just, the soil will just core through the pile? Because it will affect your driving performance. You have to check pile run. There was some soft clay in the upper part. Once you put this pile, will it just take off, or because you don't want to lose your pile? And hence, pile run had to be estimated. We also had to look at pile setup. So there's a lot, about 30 or 40 meters of clay. When your pile is there and you are welding or splicing the next segment, you want to make sure that your hammer can drive it further, right? Because it can freeze on you. Because we had the sloping on rock on Tower D, some piles might hit it. We don't know for sure, but they may hit it, and we had to consider that as well. And if it's dipping, are we going to have pile toe damage? And then pile setup. So because these piles are essentially friction piles, we expect there will be some setup after the piles were installed. Again, we had PDA testing during pile installation. Here's a typical pile group. It's got 18 piles, 4 vertical ones in the middle, and 14 on the outside, battered in different directions. Because these towers now have to take care of horizontal load, because we didn't have other foundations transferred to. The piles were between 1.22 and 1.07 diameter. We drove them up to 70 meter deep. They were driven to embedment, so we work out the frictional capacity. But if they hit rock, then you would generally have your capacity. Design loads were 10 meganewton per pile for these ones. A view photo looking west of the pile installation. So this is Tower G, the far one, and then behind it is Tower F, and then Tower D after that, and then the land. So you can see there's some piles there. The way we did that, again, we have to, this driving frame that we designed with the jackets to locate the piles, they were floated out on like a styrofoam setup. So you float this in place with GPS, and once you're pretty accurate, you drop in your vertical piles, and that helped to anchor it. Install the vertical piles, and then you batter piles. This is a view of this. So we use vibratory hammer to get the vertical piles into it, and then finally drove the piles with diesel hammer, a smaller one, compared to Tower D, where we drove the rock. Here's a view of the piles after installation. This is Tower F, looking to the west. You can see the pile groups, as well as for the 2 pile caps or driving frames, we had cross beams to join them so that they'll be steady. They'll have stability. Now, we did a pile setup, so we were anticipating it. It's a more common phenomenon. If you look at those blue piles, the end of initial driving were only about roughly 4 meganewton, and we needed 10. When we came back 15 days later, I think 3 weeks, then we got the capacity set up to over 10 meganewton. So there was a good setup of about 3 on average for these piles, which is great because you couldn't load the piles if it was in the initial condition. The 2 green piles did hit rock on F, and they had fairly high capacity anyway. And so you can see the setup was not very much. So setup is a phenomenon that we have a better handle on, but still though, to predict ahead of time, is it 2 or 3 can be quite important. It's still quite hard. Often you will almost have to do a site-specific test pile. But of course, offshore is very hard to do, and hence you have to really try and estimate and conservatively as much as you can. So those were the pile foundations that we just covered. There were 2 other issues that came up during this bridge construction that we weren't anticipating and that they got us involved. One is, remember this tower was asymmetrical and the cable had to take, the load had to be transferred to the cable. And you can imagine that single tower, only one tower, it would naturally go to the right or to the east because the weight is over there. It wanted to do that. So they realized it will happen. And so they said, well, what can we do? What can we do to bring the tower to the west by 0.5 meter, 500 millimeter? So that was the dilemma, is this tower needs to be displaced so that later on, when the load gets on, it'll become vertical because nobody wants a leaning tower there. So we decided to use micropiles or anchors. So we will bring that tower cables to land and pull them or tension them. That was one which I'll cover shortly. Then the other problem is, remember transition span? It was cast in place concrete box girders. During post-tensioning, they realized that decks were up too high by 3 inches, where it's going to connect to the suspension bridge. So they knew it's a problem. And how can they get it together before they make the final connection? And again, we thought, well, seeing we got rock in place, we use micropiles. This time we use cables, micropiles, to pull them down. Let's review how we did that. That's a single tower, 160 meters high. We use 10 200 meters long cable attached to the top of the tower to pull it back onto land on Yerba Buena Island on 10 micropiles. They were at 40-degree angle. But it was quite tricky because we had the 2 decks, permanent decks, and below that we had the temporary bridge. So we had to go through, kind of needle them through. Plus there were those cross beams every 30 meters. So their location had to be selected to avoid those, the structure we were building. When it came to land, it's just all horizontal in one row. Here's what it looks like on land, installing 45-degree drilling, installing micropiles, 10 of them. And to load up these micropiles so that we can attach to the cables that's coming down, it applies a lot of force onto the upper part, which is some soil and weak rock, fairly weak. And so initially we were thinking of 10 blocks, which would be quite neat, except the rock wasn't strong enough. So we ended up with a long beam with different heights to be able to transfer the load from those 10 of the cables onto those 10 micropiles. And we load tested every one of them because, again, there weren't that much redundancy. You had to be sure. This is a view looking down, 10 micropiles on the left with jacks, and then there's a yoke system to transfer the load onto the cable or to be able to pull the cable back. This is a view looking from underneath up, and the 10 cables going through one of those slots to the top of the tower. And then you can see the 10 cables right at the very top of that tower that you had to bring back by 0.5 meters, which eventually, when the load transfer happened, it straightened itself out. But you have to release the load slowly. Okay, the other interesting one was this transition structure. So to build this bridge, they first put in an S section. So it's like a temporary double deck section that they put on the left side there to allow traffic to go through because they did not want to stop traffic on this major bridge. So you can then see the transition span started constructing while the existing bridge was in place. So they have to transfer the lanes, the 2 decks into side by side. So it's kind of tricky geometry. And hence they went for cast in place box girders. You can see the formwork in place. Lots of vertical piles to hold them in temporary, their falsework in place. Now, when they came to the suspension bridge, which is in front here, you can see at that gap, I mentioned 3 inches too high. So those 2 decks wouldn't be able to connect with that problem. First thing they did when that happened, because that was a post-tension issue. They had lots of those temporary piles for phosphorus. They brought in 1 million pounds of steel to sit on that box girder, this concrete box girder, to try and get it down. And it wouldn't go down 3 inches. And of course, it was a concern. It's a safety hazard, especially this earthquake during that period. So hence, we came up with this micropile solution. We had to be careful where the beams are, right? To design those micropiles. We came up with 20 cables for each deck. So 2 rows of 10 on a frame, and they would go down in the certain places. You have to check. We have to check the strength of this concrete box girder to be able to transfer the load through those cables down to the bottom. At the bottom, we installed those 2 rows of 20 altogether of micropiles. We load tested every one of them. Now we use the adjacent micropiles to load test the other ones. So basically, it's all in tension. Then this way, we don't have to bring in additional piles. Here's a load test of one of those micropiles using the adjacent piles, either in tension or compression on the adjacent micropiles. Here's a view of that transition deck, the cast-in-place concrete coming towards the suspension bridges behind me. This is where those 20 cables came through the deck. This is a view where it's joining the suspension bridge. So remember, these cables were temporary. Once they formed that, the joint, the transition pore, the load then got transferred to that pier. So there's a pier just behind this. And this is what the top of the deck looked like during those process of lowering down this deck 3 inches. And there was a strain gauge on every one of those to monitor the force on those cables. All right, those some of the challenges we face. There's site conditions, the constraints that we had to face with that ended up for us to use micropiles on the steep slope, drill shafts and rock. We used the pipe piles, open-ended pipe piles driven to rock, and of course we encountered pile relaxation that we had to deal with. We drove steel pipe piles to the deep soil that we had to rely on pile setup to get our capacity. And we also used those 2 micropiles, one to pull back that tower by 0.5 meter, and then the other one to bring down the temporary, the transition decks down by 3 inches. We had to bear in mind, because this was a design-build project, the cost, the schedule, constructability, and then of course the sensitive environment that we had to work in. All those had to be considered. Anyway, it was very interesting with those issues. I'd like to acknowledge American Bridge Floor Joint Venture, the contractor for this project, as well as the staff at Concrete and Berger for working on this project. So thank you all for your attention. This is what the bridge looks like.
We will now, Dr. Science, will now take some questions for people at the University of Sherbrooke. You can also, or elsewhere, if there are other locations, you can also type your question, and Yannick will read them out. What?
Okay. Thank you for the nice presentation. I was just wondering about the force you needed to pull down the 3 inches that was applied to the piles. Do you remember how much force you needed?
Oh, sorry, I forgot to bring my notes. We actually have a paper on it.
Oh, really?
The design details. So if you just Google my name, you'll find it. Yeah, there's a few papers on it now. The most recent one, just this year, we published those 2 micropiles issue and what kind of forces we had to bring it down. It's more than a million pound force. Yes.
Thanks very much. It's you were showing us example of things not going perfect, trying to correct it. So I've got about 30 questions. I'll limit it to 3. The tower leaning and having to pull it back, the deck being too high, pulling it down with what you've tried with 1 million pounds, that didn't work at all. So
Yes.
Pull down with the anchors with 3-4 million pounds. I don't know. Isn't that inducing a lot of stresses in the structure that it's not designed for? How did we do
Yeah, no, this is why we had to strategically locate them as well. Underneath the beam, there are almost like pads on those vertical sections to make sure that they transfer the load. So our structural people had to look at that. The weight was an experiment by the contractor. So there was a separate contractor that did the transition structure. They're the ones who tried that first. It did not work. And hence Caltrans then came to American Bridge floor and said, seeing you're going to be the one responsible for that final connection pour, can you look at how we can make up or deal with this 3-inch?
Quickly, the bond strength for your piles or your micro piles or your anchors, did you use a general formula, a certain percentage of the rock strength, or you actually did accurate testing to come up with the perfect design for the bond?
Right, yeah. I'm not sure if there's any perfect design, but there are a lot of test data on San Francisco formation. The geotechnical engineer for the whole bridge, for the whole span, had already done a lot of testing, including some pile testing, because there's a lot more piles that went into the skyway section. So we used their information to design our temporary works. Except for, we did some holes on land, but out on the water, we relied on previous information. And we generally tried to be conservative because they weren't with contractors, you don't put too much redundancy. You just try to make sure you're safe, because otherwise there's a lot of cost implications if something went wrong.
Testing your anchors, did you test it to design or to 130% design or to failure?
Yeah, good question. Not to failure. We proof tested them, so typically about 110%, just to make sure we got enough beyond it.
Thank you.
Yes, Michael.
Well, thank you, Alex. I really enjoyed the presentation. I crossed this bridge many times during the construction. I saw how difficult it was and how complicated. It was very impressive. My question was, were the piles designed for uplift loads?
Yes.
Micro piles?
Our temporary piles, yes. Yeah, uplift is to be considered.
Yeah. Especially
Even on the water, it is a ship impact.
And the hammer you showed that was used for the pile driving, was that a diesel or a hydraulic?
For the offshore, for the on Tower D, the rock foundation is an offshore hammer, huge offshore hammer.
But was it hydraulic or diesel?
It's hydraulic.
Hydraulic.
Yeah, yeah. All large offshore hammers are hydraulic, the high capacity ones.
The seismic design of your temporary works, obviously it's going to be a lower return period than the permanent works, but still it's, with the length of construction that you were talking about, it's still a significant component of the design, I presume.
Correct. It's a 92-year return period. Now, I don't know why 92, but that was the return period earthquake we were provided with. So yes, we had to design for it.
And with the part of the works being on the bay muds and sedimentary materials, was it, for that particular return period, was it a question of liquefaction potential?
No, because it will soften, and we consider that, but this liquefaction wasn't an issue here. Below the old bay mud is the dense sand.
This alignment was chosen because it's not where it's very soft bay mud or there's soft or loose sand. That's why they put it next to the existing bridge. But further north, that's where you have the very soft mud and the loose sand.
But certainly the permanent bridge has a lot of seismic features. I mentioned about those 4 tapered towers. They all had shear links connecting all of them. Even all the decks for the skyway section, they all have sections to allow them to move, and they have steel going, pipes going through them. So there's quite a few innovative seismic features built into this bridge. Of course, they don't want to have another seismic problem on this bridge.
These very large piles that were driven into the bedrock, I had a couple of questions. What is the strength of this bedrock, and how far, and the second is how far into the bedrock is the actual rock?
Yeah, the good thing about, and because we knew that the bedrock was usually fractured, highly fractured at the beginning, and then it got better with depth, we knew we can get embedment. I think in terms of length, it's probably because we were looking mostly at the sound rock. It's a few meters into the sound rock. But by then, typically, we would have about 5 or 7 meters of the intensely weathered rock before it entered into the sound rock.
How strong would the sound rock be?
That's another question. It'll be hard to answer. Again, if you can, there are papers out there now that we have the UCS of this different horizon. Yeah, no, good question. Yeah, there's been a lot of, because it's interbedded siltstone, claystone, it's kind of tricky. You never know where. So when we had the relaxation, we weren't sure, is it the siltstone that's causing it, or is sandstone causing it? Is it salt water going into it? There's another theory is when you dry piles, salt water enters, is it starting to degrade it? So there's a few of these issues we could never figure that out yet. And so hence we had to make some decision to try and deal with it practically with a backup plan.
Yeah, you said that there was no liquefaction, but there was softening cycling.
Yes.
That you considered. How did you consider it? Did you do special testing on impact samples or reconstructed samples?
Right.
How did you actually get to that cyclic softening? Because liquefaction is one thing, but cyclic softening is another thing that is quite difficult to
right.
have a good idea how it's going to react.
Yeah, good question. We did not do anything real fancy. I mean, we did do some dynamic analysis, certainly for the structure itself. But remember, a lot of piles were battered piles, so they weren't relying so much on the adjacent. They're mostly axially loaded, either up or down. So yeah, we would soften the springs. That's about it. So we did not do anything real fancy on the how it would soften, other than it would soften.
Okay, so thank you very much for this presentation. At the beginning, I made a terrible mistake. I forgot to thank my employer, ETS. On my way back to my office, I'll check if my access card is still working. Usually it takes 7 days for them to have some time. And I also like to thank I can go back maybe to the sponsors. No? So I would also like to thank the sponsors, so Comtech, Turber,
KGS Group,
KGS, and Clone Krippenberger, and CGS and the Foundation for Canadian Foundation for Geotechnics. So thank you very much. Thank you for your.
Mario, ouais, comme tout le monde ici, je vais me permettre de prendre quelques minutes. François, si tu veux bien. Très belle présentation, merci beaucoup. Plusieurs d'entre nous étaient la semaine passée à la conférence à Edmonton, Geo-Edmonton. Ça a été vraiment très plaisant, on a appris beaucoup. On a surtout eu du fun, ça a été du bon networking. Ça a été une des conférences où on a eu plus de fun là-dessus. Que tu as manqué d'ailleurs, mais merci qu'on a eu du fun. J'ai eu la chance, je suis président EDEC pour entrer en fonction en 2019, et puis j'ai eu la chance de présenter pour la première fois notre nouvel exécutif. On a gardé Kent Bannister à la finance, Rob Kenyon comme VP technique. C'est des VP techniques, entre autres, qui organisent le Cross Canada Lecture Tour. Il y a beaucoup de travail, donc c'est une très grosse organisation pour venir présenter des qualité comme ça. Et aussi, je suis extrêmement fier de présenter pour la première fois au grand public notre nouvelle VP Communication et Services aux membres, your own Judith Bouchard. Judith va nous aider à marquer nos objectifs, c'est d'être de plus en plus présent à la CGS nationale avec les comités locaux, de former une grande famille, d'avoir une plus grande présence. Et toi, tu as déjà été présidente, tu vas nous aider à accomplir ça.
Je connais la réalité des sections, du moins de la nôtre.
Donc, on vous invite à renouveler, si ce n'est pas déjà fait pour cette année, au moins l'année prochaine, le membership de la CGS nationale, qui est distincte de la CGS locale. C'est deux organisations quand même différentes, mais c'est vraiment important que vous supportiez la CGS nationale parce que ça va beaucoup de services. On va se faire un sales pitch, mais c'est reconnu à travers le monde. On va aussi refaire le manuel canadien des fondations sur plusieurs chapitres. On va chercher des volontaires. Si vous pensez que vous pouvez avoir votre implication et laisser votre marque sur ce fameux manuel de réputation mondiale, on vous invite à nous joindre, Judith. Et toute cette organisation-là tient à une cohésion des yeux, tient grâce à une extraordinaire talent de notre directeur exécutif, Michel Oakland. Merci beaucoup. C'est assez pour moi.
Oui, mais vous avez oublié quelque chose.
Ah oui?
Non, parce que c'est la première réunion de la section locale depuis que M. Albertin a gagné la médaille Leggett. Donc, ça n'arrive pas souvent qu'un membre de la section locale gagne la médaille Leggett. Donc, je pense qu'on peut en profiter pour. Merci beaucoup. Merci, François. So sorry for the last part in French.
I kind of know what's going on. I'm the CGS, he's executive. Yeah, sure.
Are you free to have dinner with Alex? Tonight? Judy? That's okay. We'll see Ellen, maybe Yannick.
Plenty of success with the rest of the tour.
Thank you. Good to see you.
Okay, nice to see you too.
Oh, yeah.
Ben non, mais vous aussi, ça vous dit.
Ouais, non, ouais. Non.
C'est vrai, c'est aussi on commence à avoir le temps de plus. Moi, j'ai pris un rôle par dernier pendant que dans une particulier aussi. Ouais, non, c'est le fait de le faire. Encore là, ça se peut que je tourne un petit peu moins longtemps. Oui. C'est moins que la dernière.